model is very robust. All of our courses are available online, so you can do our courses from anywhere. You don't have to travel. Labs are done through remote and virtual labs and allow you to access real world scenarios from your desk. Um, that's it for this page. If you have any questions about this later on, you can definitely ask me. Before I introduce Dr. Jacobs, just a quick reminder, we will have a fact QA at the end of the session. So any technical questions, please hold those till the end. And Dr. Jacobs, on to you.
Thank you. Thank you so much, Maria. It's an absolute pleasure to be working with you this evening, and I appreciate all of the effort that you have gone and put in. Welcome, everybody. I'm based in the middle regions of South Africa, and I can see that there are a number of South Africans out there. Great to have you all present. I see we've got people from Trinidad and Tobago as well. It's wonderful to be joining all of you. I'm going to try my very best just to share my application with you. And let's first see that that is going to get across to your screen. It looks like it's busy at the moment. I'm just going to try and see if that's going to come across. If it doesn't come across, Maria, I might just ask you to stop sharing your screen, and then we can try to get mine across. And if that doesn't work, we'll have another plan up our sleeve. Let's go and see if I can get that screen coming across. It's got to shoot across somewhere at this point in time. Let's go and have a look what's happening. Share the files. No, I don't need to go and share the files. I want to share the screen with you. Somehow something is happening at this point in time. We're getting some type of a reconnection. I'm just trying to see what's happening over there. Let's go and try that again. Okay, my screens are there. My slides are there. Absolutely fantastic. Thank you. Now, we are going to deal with what is referred to as process control tonight, and everything should work out perfectly. We did one of these the other day, by the way, and we had over 500 delegates that were logged in. Tonight we are 73, so I don't envisage any problems at all. Process control is really a way of life for all of us. And you can think of just about anything that's going to be controlled from that respect. You know, if I go and think in terms of something such as my motor vehicle has got a cruise control put into it, or speed control. I go and set it. In this country, we can travel at 120 kilometers per hour. I go and adjust it. That target value that I'm going to go and adjust it to is what we will often call in instrumentation the set point, my target value. And then, of course, my vehicle needs to go and measure the speed at which it is traveling. And from our point of view, we're going to refer to that as the process variable. So let's go and have a look over there. Right, exactly, very important. Thank you. Thanks for those comments, Charles. Charles, so we have to go and Charles, we have to go and make sure that we can get all of that sorted out. Now, as I say, there's going to be many forms of control that you and I can go and implement. How about something such as a level control? Maybe I'm going to have a tank out in the field, and this tank of mine is going to have a level that I would like to go and control. I would have to go and put all of the instrumentation in place to go and do the level control for me. I'm just going to put a little bit of water inside that tank, and that's going to do the trick. Right, so for our point of view right now, I probably need to have a level transmitter that is going to measure the value that we have got out in the tank itself. That signal might be something such as a 4 to 20 milliamp signal. Now, this is where my process control comes in. I'm going to sit with my level indicator and control right over there, and let's go and put in a variable speed drive on the system. My controller would then have to go and be connected up to the variable speed drive that we have. have a look at how the terminology that we've just gone and used is going to come into play. If I was to talk about the fact that I am measuring the signal from the level transmitter, that is going to be known as my PV, or my process variable. The signal that I'm going to be sending out to control the variable speed drive is going to be known as my output. And then, of course, I've got a lot of hands that are getting raised, but if there's any questions, please do type them into the chat box. I will pick them up straight away. And then, of course, I need to have a target value at which it's going to operate. And that's going to be my set point. So when I start to talk in terms of process control, you and I might decide that we would like to control that tank at 75%. I therefore have to go and give it a set point of 75%. That becomes my target value. Now, as I measure the value out in the tank, my process controller is going to respond accordingly. If I was to go and measure a value of 73%, then my controller knows that I am below the target value, and it will then go and send a signal to the variable speed drive to slow down just a little bit. And by the variable speed drive slowing down, the level is going to rise and get very close to the set point. Or just the opposite. If my level was sitting at 80% over there, now all of a sudden I am above the set point. My controller knows to send a signal to the variable speed drive so that I can go and speed it up ever somewhat, and then it's going to drop the level down to 75%. So there's many different examples where you and I can go and do process control out in the field. It can be as simple as you like, and it can be as difficult as you like. This gets me to the next of my slides, which is going to speak in terms of the type of control which you and I are going to get. Again, it's going to be up to your system. When people talk about the fact that we're going to have a bad control, it really just means that my target area is sitting over there, and I might be going quite a bit above the target area, or it may be that I'm going quite a bit below the target area. Sometimes it's okay for you to live with it, sometimes it's not. If you can hear me clearly and if you can see my images, can you please just type in the number 2 on the screen, and that will know that everything's perfect. But of course, there's everybody that doesn't have any sound. It's going to see all of these 2s, and they're going to wonder what on earth is happening. Okay, thank you so much. That just gives me peace of mind. Now, you know, sometimes we talk about the fact that bad control is going to deviate from my set point. It might not be a very bad thing. Maybe I should first go and speak about the different types of control that we can get, and then I'm going to come back to the bad control and the good control. You're going to hear people talk about the fact that we can have open loop control. You're going to hear about the fact that we can have closed loop control. Some of you are going to speak about the fact that we can have feed-forward control, and some of you are going to speak about the fact that we can have feedback control. I'm going to go and put it down over here. Feedback control is actually going to be closed loop control. So let's go and put this down. It's closed loop control or feedback control. These are the most important forms of control which you and I can go and utilize out in the field. And every one of them has a time and a place in industry for us to go and use. How about open loop control? You know, if you were to go and wake up in the mornings, thank you very much for that confirmation, and maybe you're staying in a hotel room or something along those lines, and you pop down for breakfast, they're going to have a toaster standing in the breakfast area, and that toaster is going to have a little dial which you and I can go and adjust. And all that we do is we pop our piece of toast in there, we pull the button down, and it starts to do what it has to go and do. Now, depending on the setting that you've made, we're going to find that different colors of toast are going to come out of the system. If I have gone and set it with a very light setting, then I'm going to get a piece of toast that comes out that's lightly toasted, or I might go and set it for a little bit of a stronger setting, and then my toast is going to be somewhat darker, and you think you can get that thing to change the color, that looks better. And if I really go and mess it up, then I'm going to end up with a piece of toast that's not going to look too good for us. It's going to be very, very black. Now that is an open loop control. When I talk about open loop control, what I'm saying is I give an instruction and I walk away and I don't worry about the repercussions. That's what I'm doing with my toaster. I push the button down and I walk away. Usually an open loop control is going to operate with something such as a timer. You think of your automatic dishwasher. You think of your automatic washing machine. They're going to work with a timer. I've got exactly the same, and I know that when I get into the house after this, my wife's going to say to me, have you sorted it out yet? At home, I've got an automatic sprinkler system in my garden. It sits over there, and every day at 1800 hours and no minutes and no seconds, that system kicks in and starts to water my garden. It does a certain section for 5 minutes and another section for 10 minutes. It is an open loop control. When it gets the signal to run, it runs, regardless of whether we are in the middle of summer, or if we are in the winter, or if it's raining outside, or if it's dry, or if my mother-in-law has come to visit. It doesn't make a difference. We're going to give it an instruction and we're going to walk away. That's what an open loop control is. Now, most of the control that you and I are going to deal with is going to be a closed loop control or a feedback control. One day when I get to writing my book, Rodney Jacobs' Idiot Guide to Instrumentation, I'm going to explain it as feedback. Closed loop control is when I measure something to control that same something. I gave you the example at the beginning of our session where I said that my motor vehicle has got a cruise control or a speed control built into it. I measure the speed of the vehicle to control the speed of the vehicle. The example that I gave you a couple of minutes ago, I measure the level to control the level, or I'm going to measure the pressure to control the pressure, or I'm going to measure the flow to control the flow. That is going to be my closed loop control. Now, on the right-hand side of the screen, you can see a more advanced form of control, and that is going to be known as feed-forward control. Not too many of you are going to use this, but it does play a role in our lives. With feed-forward control, I might measure something to go and control something else. I'm going to go and control a process based on a disturbance. That's it. That's going to be all of my control. I'm just going to have a look at the disturbance. Let me give you an example as I sit here and think about it. What if I have a tank? There's my tank. And I want to control the level inside the tank using a variable speed drive. But does it use relays or does it interpret the signal or a PLC? Hello, I'm going to answer your question over there. Okay, so please hold that question of yours for 3 minutes and 23 seconds, and I'm going to answer that one straight away. In the case of feed-forward control, it measures a disturbance to my process. I can have a pipeline coming in over there, and let's go and say that I put a flow transmitter onto that signal. Now that flow transmitter is going to send an analog signal out, a signal that's going to vary from 0 to 100%. I can take that signal to, I'm just going to go and use your feed-forward controller. For those of you that are very advanced in the field of instrumentation, you might say, Rodney, that stands for a fractional flow controller. Don't worry about that. I'm just, at this point in time, indicating it as a feed-forward controller. And that is going to be connected to my variable speed drive. So what's going to happen in this case is I'm going to measure a disturbance to my tank. If the flow increases, I can run the variable speed drive faster to compensate this. If the flow happens to decrease, I can run the variable speed drive slower to compensate for that. I am measuring one thing to control something else. I'm going to, in this case, be measuring the flow to control the level. Please note that in order to do this, we need to have a model of the process. I'm going in a totally different direction here. I'm just doing this as the slides lead me. I need to have a model of my process, which is going to be built into the controller. And that model of the process will consist of 3 separate aspects. I'm going to have the gain of the process, the dead time of the process. The dead time is the time that elapses from when I change an output until I see a noticeable response. And then I'm going to have the time constant. The time constant is going to be the rate of change of that process. Now, I know that Kabu is waiting very, very patiently for the answer. And in this case, we need to go and interpret that signal. Kabu, what I'm going to do is I'm going to get to the little circle that I made for you. And remember, that is on the page of the closed loop control. God knows, Sarah, is it possible to get losses in a closed loop system? Well, it's not going to be losses per se, unless it's going to be a loss in your signal. What's going to happen is your control may not be as good as it should. And I'm going to get to a block diagram to go and explain that to you. Thank you. Keep those questions coming all the time. And Maria's got them sorted out in the background as well, just in case I'm too slow to go and pick them up. Right, let's get to that closed loop control. If you don't mind, I'm going to use a new page. So that is my closed loop control, or my feedback control. Closed loop control can be done in one of 2 ways. I might have on-off control, or bang-bang control, as some of the people would refer to it, and I could have regulatory control. It does not mean that one is better than the other. It just means that one is going to be appropriate when I want to go and use it. Let's go and have a look at the on-off control. I've got a tank, and my electrical colleagues go and put these little floater balls into the tank itself, and I'm going to have a pump at the bottom. And what's going to happen is when I get to the high level over there, my pump is going to start to run. And when I get to the low level over there, my pump is going to stop running. So I can run it and I can stop it, and I can run it and I can stop it. My level is actually changing between that point, which might be at 90%, and that point, which might be down at 20%. My level is going to go from 90% to 20, to 90% to 20. In other words, what my level is going to do is, as the level gets high, I'm going to start the pump, and the level is going to drop down until I get to that 10%, and then the pump's going to stop, and the level is going to start to rise up. And when I run the pump, the level is going to drop down, and then the level is going to rise up, and then the level is going to drop down. These are 2 digital signals that I'm going to feed into my PLC. Kabu, does that explain it? So my PLC can work with on-off signals. Now, just to get back to my slide, is that not going to tie in with that form of control on the left-hand side? My level is going to vary between 90% and 20%. It's not a bad form of control, but it's going to give me quite a large variation. Okay, now if that's not good enough for you, then maybe you're going to go and have a look at the regulatory control. Regulatory control is when I control an output anywhere between 0 and 100%. Maybe I've got a control valve on my line, and that valve is going to be opened or closed. If I go and open it up a fraction, my flow is going to increase. If I open it up some more, my flow is going to increase a lot more. If I start to close it, my flow is going to start to decrease. That becomes the regulatory control. I can take it anywhere between 0 and 100%. And this starts to tie in with something that I will be speaking about very, very shortly, and that is that we are going to go and put a controller in, and that controller is going to be known as a PID controller, proportional, integral, and derivative. And that's the way we're going to go and start to control our process. God knows I have not forgotten about your question. I'm working towards it. Let's go and get a brand new page. Folks, I hate death by PowerPoint. I hate to put up slides and you have to read the slides and look at that and look at this. This is the way that I present. I prefer to be very active, drawing my own pictures, if you don't mind. Right, let's get back to a brand new picture. So what happens with my process, and why do we start to have a look at if there are going to be any losses? My process is sitting right over there. That's going to be my plant. Maybe I am controlling a level or a temperature or a pressure or a flow. That is my process. I'm going to have some or other instrument that is put in place, and that instrument is going to go and measure my signal for me. Now, that instrument will send an electrical signal, which is now known, as we've said earlier tonight, as my process variable. And that could be something such as a 4 to 20 milliamp signal. And this is going to come to my controller. I'm going to put in an arrow over there. Now, have a look at what I'm going to go and do. My controller is going to, in this case, be negative feedback, a closed loop control. My controller is going to have a target value known as the set point. And it will compare the process variable to the set point. And if there's a difference, it's going to calculate it as the error. The error is the process variable minus the set point for a reverse acting controller, or the error is going to be set point minus the process variable for a the other control that we are going to go and have. So it's going to come in that respect. Now, inside my controller, and I'm going to go and put the controller in over here as a box, a red box. Let's just go and put that as my controller over there. So inside the controller is going to go and see if there is an error. We're going to put that at the top of the page. If there is an error, the controller is going to go and calculate an output, and that output is going to be based on the PID settings that we have gone and put in. Right, now, that signal, that output signal is going to go to my final control element, my variable speed drive, or my valve, or my actuator. That's going to be the final control element, and that's going to have an influence on the process. The question that God knows asked was, can we have losses in a closed loop system? Well, if that's going to be a 4 to 20 milliamp signal, what I put in is what I'm going to go and have out. It's going to go out through the system perfectly. That's probably going to be a 4 to 20 milliamp signal, and that's going to have an influence on my process. The only losses I could have would be physical losses. If I've got a hole in my pipe, or if this tank happens to overflow, and that's only going to be because of bad tuning, then that can come into play itself. Otherwise, it's going to control itself very, very nicely. So the valve control itself in regulatory is manual only, or maybe automated as well. Very important point that you've gone and raised there, Charles Brunt. In this case, what is the difference going to be between automatic control and manual control? Let me go and show you. If I have a tank and I've got a valve going to that tank, and I want to control the tank level, then my operator is going to go and sit there. The operator will look at the level inside the tank, and he or she will open or close the valve as required. Because there is a human involved, we're going to refer to that as manual control. That's it. The only time that manual control comes in, I'm being very sexist when I look at the word man in the front. I shouldn't be doing that. I've never seen it in my life before. But manual means person. When there's a person involved, it's going to be manual control. I can have exactly the same thing. I can go and put in an automatic control over there, and I can have an instrument, my level transmitter, which is going to send the signal to my level indicator and controller, and it is going to control the valve. I don't have any manual or human intervention now, so that's what it's going to be called automatic control. It's as simple as that. When I have people involved, it's going to be manual control, and if I've got a computer or a PLC or a controller making the decision, it's going to be an automatic control. Right, Esther, I can see a question that's come through from you. I have an issue with density control valves not getting linear control. That's a very interesting point that you've gone and raised, and you are getting into advanced control right now. These questions are keeping me on my toes. Thank you very much. You know, if I was to have a tank shaped like this, which we often going to have in the oil and gas industry. And if I maybe got a valve that is coming in and I'm trying to control the level inside that tank, please remember that here at the bottom, if I open up the valve, it's going to fill up very, very quickly. However, over there, if I open up the valve, it's going to take a lot longer to go and fill up that tank over there. And when I get back to the top of the vessel, I'm going to have just the opposite over here. So right at the top over there, we're going to go and find that if I open up the valve, it's going to fill it up a lot quicker again. This is a non-linear process. And this is going to tie into what you've gone and referred to there, Esther. That's a very sophisticated form of process. So what we do is we usually go and take our process and we divide the process into different zones, and we go and put in a controller that will control it for us. My controller will use one set of PID controls over there. It's going to use another set of PID controls over there, and it's going to use another set of PID controls over there. We can go and set the systems up to do this for us, and then that is going to be known as an advanced form of control. I've brought up a simulator on the screen, and I'm just going to go and show you that the word schedule. This is where we're going to refer to this as gain scheduling controller. I calculate what my PID values will be, and then according to that, I let the controller go and get different PID values in different parts of the plant. Okay, thank you very much for those questions. I'm just going to keep this out of the way. I want to get back to that very, very shortly. Now, when I start to look at a controller like this, then I'm starting to get automatic control. And then I can start to go and do this type of control, where I am a lot closer to set point with my regulatory control, where I might go and put in advanced control, and then I'm going to be a lot closer to the set point. I put in a set point of 75%, and it goes to 76, and it goes down to 74. I'm going to have very, very tight control. That's going to be more important type of control. Yes, that's what it's going to go and boil down to itself. Right, the question from Timbu said, is SCADA an automatic or a manual control? Let me go and put that into perspective, and then we can take it from there. When we talk about a SCADA system, my operators sit in a control room in front of a computer screen. That computer screen is often going to be known as an operator workstation, or it's going to be known as a human-machine interface. That is the eyes and the ears of my operator into the plant. Now, the operators will have numerous screens. There is a second one in the control room, and there's going to be a third one in the control room. Let's go and say that there's one in that control room, and there's going to be one in that control room. All of these computers are linked to each other by means of a network cable, and that network cable is then connected to a very important computer system known as my master station, which could be one of the other computers, but I'm going to go and put this down as my master station over there. So that's going to be that computer, master station, and that computer in turn is going to be connected up to a network, which is going to go to my PLCs out in the field. My RTUs is the fancy word. There can be a PLC, and there can be a PLC, and there can be a PLC programmable logic controller, and there can be a PLC programmable logic controller. Right, now this is actually known as my SCADA system. The total system is known as a SCADA system, or a distributed control system, DCS. The difference between DCS and SCADA actually lies over there, because in the case of SCADA, I can send the information over long distances. 1 kilometer, 10 kilometers, 100 kilometers, 1,000 kilometers, 10,000 kilometers. Absolutely correct. SCADA stands for Supervisory Control and Data Acquisition. Now, to get to your question, Timbu, the operator sitting over here can, for example, have a level control that's sitting on that PLC over there. If the operator puts that control into manual, then they're going to have to change the output from 0 to 100%. Then it's manual control. If the operator sitting over there puts that controller into automatic, then the PLC is going to go and control the output itself. So your question was, is SCADA an automatic or a manual control? SCADA is what you want it to be, but it's going to be consisting of automatic data collection. Supervisory control and data acquisition means that we're going to collect information and send it out. That's all automated, but the control is then going to be for you itself. Shadrach, what is the difference between DCS and SCADA? DCS is all on one geographical site. SCADA tends to take us a bit away from the site. We have information that needs to be sent across an unprotected, potentially unsafe, potentially slow network. That's it. SCADA is the same as DCS, but DCS is on one site. SCADA is going to be over a wide. Those are going to be the differences that we can go and encounter. Right, I'm going to get back to my slides. We've now gone and spoken about the different types of control that we can have. This is my plant. Anything that affects my plant is going to be a disturbance. How about if you and I are going to try and control the level inside the tank, but I have pipes coming in which I'm not monitoring, but they can cause the tank to overflow. Any disturbance is then going to be any disturbance that is not measured is what we are going to refer to as a disturbance that we can go and work with. Samuel, you say, what are interlocks in control? If I was to have a start-stop process, if my system has no vibrations, and if it is not over in temperature, and if this switch happens to be in the right position, and if I do happen to have the right air coming in, I'm going to bring in my interlock relay over there. And once the interlock relay is okay, then I can go and operate the rest of my circuit. So an interlock is just going to lock out certain sections of my plant for me. Remember that we spoke about PID control, and I said to you that the controller is going to have a limited error. The error is the difference between the set point and the process variable, and that's what it's going to do to go and control my process. I can have different types of processes. Often we're going to have a process which is going to be resistive in nature. You know, I'm trying to put steam through a boiler, and I've got a very thin pipe, and that flow has to make its way through that pipe against the resistance. Or I'm going to go and put a control valve in the line, and that's going to provide me with a certain amount of resistance. That's going to be the resistive part of the process. We can also have the capacitive part of the process. A small tank is going to fill up a lot quicker than a big tank. So that becomes the capacitive aspect that can go and fit into the process. Often you're going to hear people talk about a first order process or a second order process. It's pure academic. In the case of the first order process, what's going to happen is when I open up the valve over there, my process responds immediately. That's going to be a first order process. However, if this tank is connected to another tank and I'm trying to control the level in that tank, and this tank has to first be controlled to get that tank to go and get controlled, then my process team seems to respond in a more S-shaped manner, and that becomes the third order or a second order process. Erasmus says, is it advisable to use power relays in place of interlocks? It's entirely up to you, but please remember, if you are going to have a safety system such as an emergency stop, then you have to have it hardwired into your system. You can't go put it into a PLC. You can put it into a safety PLC, but not a normal PLC. It must be hardwired into your emergency system. Right, there's my second order process that we've just gone and spoken about. Now, I said to you that feedback control could be on-off control or it could be modulating control. In the case of modulating control, we're going to be putting in a PID controller. Maybe I should go and demonstrate a PID controller for you. I'm going to say process, select a model, and in this case over here, I'm going to go and use the generic model. Open that up over there. These are all on our remote labs. If you do go and do an EIT course, you can actually get to these pieces of software that we have got. I'm just going to go and make sure that I am viewing this in minutes, and I'm going to go make sure that I'm viewing it in percent. Okay, now this gets to the three types of control that you can go and put in. I'm quickly going to go and press the control button and have a look at the control options, and let's quickly go and do a proportional control only. Proportional control. Right, I'm going to go to the tuning parameters, and let's go and set that value to 0. And I'm going to go and set a gain of 1. Now, what the controller is going to do right now is if I put it into automatic, remember the questions that you asked earlier, automatic or manual, I put the controller into automatic, and look what's happened. My set point is sitting at 50%, but the process variable has gone and run somewhere away. And that's purely because this is a mathematical calculation. Whenever I do P control only, I'm going to have an offset. My process variable does not get to the set point. I can go and change the set point. My process variable will get closer, but I'm always going to have an offset. I can go and put in a larger gain. Let's go and put in a gain of 2. And what will happen is that my final control element works harder. The offset gets smaller, but the offset does not go and disappear. I can go and put in a larger gain over there, and the offset is going to get smaller, but the offset is not going to go and disappear. Now let's go put this in perspective. If I talk about the P point, the P type of control, the advantage and the disadvantage is that this is my main form of control. When you ride your vehicle and you push the brake pedal slightly, the car starts to slow down. If I push the brake pedal down very hard, the car screeches to a stop. It's based on the proportional signal that I've gone and set it. Most controllers are going to use P control. Disadvantage, it's always going to give me an offset. You saw that. It did not get to the set point. Now this is where we bring in the next form of control, which is going to be my eye control. I'm going to go back to this controller and close it and start it up again from fresh. And I'm going to go and show you how we can go and do the eye part of PID control. There is my controller back on the screen, and I'm going to use exactly the same process, which is going to be my generic process right over there. And in this case, let's go and turn that to view the percentage of the display range. And I'm now going to go and I'm going to tell it to do eye control only. It's going to do integral control only. That's going to be it. Now let's go and give it an integral value. Maybe I'm going to go and put in an integral value of about 50. Okay. Now look at what's going to happen. If the controller is in automatic and I change the set point, my controller will then go and change its output to get to that set point. Why is it jumping all over the place? Because I am working with integral gain over here. So that should be just the opposite. 100 divided by 50. I should have put in a value of 2. I didn't realize that it had that setting over there. Let's go and put in a value of 2. Let's see how that is going to go and work. That should be a lot better. I'm just going to go and stop this quickly, stop the controller and open it up. I didn't realize I was looking at the wrong settings. Let's go and put that value in quickly. And where's it gone? It's gone to this page over here. It's going to bring it back for us to have a look at. And in this instance over here, I'm just going to go and say control. And my control option is going to be integral only. Let's go and put that one in to the controller itself. I'm then going to go and put the controller. It doesn't make a difference if it's auto or manual. It doesn't make a difference at all. I'm going to go and put in the tuning parameter of 0.04. Okay, let's go and put that in. Now, if the controller is in automatic and I go and change the setting, what happens is that my output keeps on changing until I get to the setting. So that's the purpose of integral action. It's there to get rid of the offset. Look at that. I've now managed to get to the setting. I can make it faster if I want. Let's go and put in a value maybe of 0.16. I'm going to make it faster. And now when I change the set point, it's going to move a lot quicker, but the faster it moves, the more unstable the process becomes. Imagine this is my level that I'm trying to control. You see how the level has gone and got a little bit unstable. But it's going to sort itself out anyway. So this is going to tie in with what you and I would go and do. The integral is there to eliminate the offset, but the disadvantage is if it make it too fast, my process becomes unstable. Okay, and we teach you all of this when you actually are going to go and do the course itself. Are set point values the same as system parameter threshold readings? No, they're not the same. Set point is my target. Set point is where I want to operate my process. The other values are going to be different values that we can go and measure. Every process will have a target, and therefore every process that is automatic is going to have a set point. But those processes will go and measure different values. If you and I are driving our vehicle, I want to get back to my signal that we are going to have. Samuel, the problem is on your side because everybody else can hear me. I'm just going to go and put this over there. Can't hear me, Samuel. Problem on your side. Okay, apologies for that. It's not on my side at all. Thank you, Maria. Thank you for catching that out. You know, if I'm driving my car, don't I use integral action? When I'm riding with my car down the road, and there is the lane that I'm in, if I start to stray out of the lane, I correct myself and get back into the lane. If I start to stray in that direction, I correct myself and get back into the lane. That's where you and I are going to go and use integral action in real life. Now, I'm not going to have the time to demonstrate derivative action for you, but derivative action is a very intelligent form of control. What it does is it provides us with dynamic stability. In other words, it's going to outguess the process. It looks at the rate of change of the process variable, and based on that, it will open or close the valve quicker to get the process more stable. That's what derivative action is going to do about. The disadvantage of derivative action is if I have any noise on my process variable, any unwanted signal, that noise is going to be multiplied through to the final control element, and that is going to be the problem that we are going to go and encounter. So that's PID control in a nutshell. I've just gone and shown you a very basic introduction to that. Great, I'm keeping an eye on all of the questions that are coming through, and I'm going to get back to my slides. Let's go and see where I am sitting with my slides. Okay, that is it. So when we go and do regulatory control, I'm going to have a controller, and that controller is going to have three settings: proportional control, integral control, and derivative control. And this is what we are going to go and work with. Now, I can go and use proportional control on its own. I can go and use integral control on its own. I can use a combination of proportional and integral. I can use proportional and derivative. And I can go and use full PID control. I just cannot use derivative control on its own. Okay. In this case over here, for example, PI is going to be used with very fast processes, maybe something such as a speed control. In this case over here, PID is going to be used in very slow processes, maybe something such as a temperature or a PID or a conductivity that we can go and work with. That's going to be the difference that we can encounter. You look at your process and then you decide what you are going to be putting in place. You know, some of you might even hear people talk in terms of a cascade control. In the case of a cascade control, I've usually got one controller built into another. How about if I have a boiler sitting over there, and I have got cold water coming into the boiler, and I would like to have hot water coming out of the boiler. I can bring in steam. That steam is going to go through a control valve into my boiler, and I can go and use that to control the flow. I've got a temperature transmitter, which is connected up to a temperature indicator and a controller with a set point, and that is going to operate my steam valve over there. Now, sometimes that may not be good enough. Sometimes I might have a disturbance on my process, such as the pressure that goes up and down. In cases like that, I might want to put in an extra controller. How about putting in a flow transmitter over there and putting in a flow indicator and controller? And that's going to operate the valve, but this one's set point is going to come from that one's output. This becomes known as a cascade control. Many of you may hear about a cascade control in the field. I'm going to give you the Rodney Jacobs simplified image. In the case of a cascade control, there is going to be my temperature controller, which will have its own process variable coming in, which is going to be the temperature, and it's going to have a set point. The output of that controller is going to be connected up to the set point of this controller, which is going to be my flow controller. My flow controller is going to have its own process variable coming in, which in this case is going to be the flow, and this controller's output is going to go to my final control element. That, folks, is known as a cascade control. Some of you might be familiar with the names that get used. This is known as my master, and that is known as the slave. Heaven forbid we use that term in South Africa, because we come from a very bad past, and they say that that's going to be colonial. We don't do that. So maybe you're going to go and call this your primary controller, and you're going to go and call that your secondary controller. Or you can call this your outer controller, and you're going to call that your inner controller. All just different terminology that we are going to use in the different places. Now, I've spoken about the fact that we can have direct and reverse control. Let me show you where this is going to come into the greater picture. I'm just running out of pages, and I'm just going to go and do file new. As you know by now, I don't do get by PowerPoint. I like to do my own pictures. What if I was to have a tank, and I have a valve sitting over there, and this valve is going to be air to open, spring to close. If I give this valve any air, it's going to open up, and the level inside the tank is going to go and rise. What if I was to have the same valve put in over there? In this case, it's also going to be an air to open, spring to close. If I was to give it air, it's going to open up, and now my level is going to drop in the tank. So the controller that I put in there must be different to the controller that I put in over here. The one needs to be direct, and the other one needs to be reverse control for us to go and get that to work. What are the basic final control elements in a refinery plant? Shadrach, how about something such as a control valve or an actuator connected to it? Or how about something such as a variable speed drive connected to my pump? Those are some of the control valves. The final control element. The final control element is whatever I manipulate to ensure that the process is going to work exactly as it needs to go and work for us. Right, feed-forward control. We spoke about that one earlier, but we've already got this covered. Feed-forward control is when I look at one thing to go and control something else. That's going to be a feed-forward control that we can go and encounter. Now, during our training, we are going to go and show you how to calculate the PID values of your controller. That is going to be referred to as loop tuning. Wow, look at our numbers. We've jumped up to 87 at this point in time. Loop tuning is when I go, sorry, I just want to stop that and I go to how the page it does that. Loop tuning is when I go and adjust the proportional value, also known as the gain, or I go and adjust the integral value, also known as the reset, or I go and adjust the derivative, also known as the derivative. There are so many different controllers that we can use. There are so many different techniques that we can go and use for loop tuning. I don't have the time to show you a formalized session because I'm getting close to the end of my section. But what I'm going to go and do is I'm going to show you how we can tune a process using trial and error. I'm going to take this controller of mine. Let's just go and put this into a percentage. And I'm going to go and put in a low gain. Maybe I'm going to put in a gain of 0.5. I'm going to accept that. Yes. My minutes per repeat have been switched off, and my derivative has been switched off. Now, if the controller is in automatic, and I give it a step change, you can see that the process is going to respond. And it's pretty sluggish. So what I can go and do is I can go and increase the gain. Let's go and try a gain of 1. And I'm going to look at the dynamic response. Let's go and see what my process variable is going to do. My process variable has responded, but I can probably have it a little bit faster than that. I'm going to go and put in a gain of 1.5. Okay, that's going to be it. Right. Now, if I go and change it, you can see that the process is going to have a certain amount of behavior. I haven't used a calculator, nothing like that at all, and it's doing what it has to go and do. Next, I can go and think in terms of putting in the integral value. So just go and see what I'm working with over here. I am working with minutes per repeat. Okay, so hopefully if I go and put in a value there of about 70, let's go and see what's going to happen. Now, when I go and activate the process, the gain kicks in straight away, and then my process variable is going to start to take away the offset. It's going to eliminate the offset. Am I running here with a full PID control? I want to just go and see, yeah, it's doing it very, very slowly. My control is going to be set at PID non-integrating. That's perfect. It's very slow. I can probably go and make it faster. Let's go and take that down to a value of 40. And I'm still not using a calculator. I'm just using my experience. And now you can see when I do go and put it into automatic and give it a set point change, my process is going to respond. The PID value kicks in. And once the P part kicks in, and once the P part is finished, round about now, my integral value starts to kick in, and that's going to start to eliminate the offset. It's still a slow field process that I've got. Let's go and try that down to a value of about 10. Right, now let's go and see what's going to happen. I give it a step change. The P part kicks in straight away, and then the I part is going to kick in and take away my offset. And that's it. The derivative action is to make it very, very smart. I can, for example, go and put in a derivative value, and what's going to happen now is that it's going to give me a lot smoother but more effective process. That is a very quick way of tuning a PID controller. There are more formal methods such as Ziegler-Nichols, which I'm going to teach to you if you do come and sign in for our workshops. Right, so that is what loop tuning is going to be all about. Lastly, please remember that we do have auto-tuning controllers. These controllers, when you push a button, are automatically going to go and set their PID values. I kid you not. They do that automatically. You and I don't have to go and do that at all. And that is where I'm going to end my section of the webinar. I hope you've enjoyed this. And once again, I would like to say a huge thank you, Maria, in the background for everything that has been done. Maria, I'm handing over to you. Thank you so much.
Thank you very much, Dr. Jacobs. That was super interesting, and that was also in the comments as well from our students, how well this was covered. So thank you so much for that. For everyone, we are going to do a quick Q&A in just a moment. These are our courses that cover this topic, so if anyone is interested in that, please sign up. As Dr. Jacob mentioned, the software needed for any of these courses are included in the course cost, so you don't have to pay extra for software. You don't have to go find it yourself. It is available to you. I'm about to post a link in the chat box. This link will take you to all of our instrumentation, automation, and process control courses. Please take a look at that, and if you're interested, take a look at the entry requirements, and we hope that you'll join us. Joe, the slides, everything will be distributed to the attendees. It does take a couple of days, okay? Here is our upcoming courses for the next upcoming courses at EIT. These will be in the slides sent to you, and with these additional links. So, like I said, give it a couple days. That will come to you. Here are our upcoming events, and just like you signed up for this one, you can go onto our website and sign up for any of these coming along. I'm posting a link to access your the form to receive your certificate of attendance. This QR code also works. So I'm going to leave this up for just a little bit and open things up for Q&A. Does anyone have any questions for Dr. Jacobs that he didn't already cover? Yes. Dr. Jacobs, could you explain why ID controller doesn't exist as well?
Right, you can use an ID controller. Thank you very much. ID is going to stand for integral as well as derivative, but remember that the integral part is really going to be very, very slow. And so we're going to try and just get the offset removed, and then of course the derivative kicks in. By the way, the derivative action is going to kick in first. So what will happen is that the derivative action will kick in and then the integral will come in. You're going to use that on a very specialized controller. If I was to go back to the cascade loop that we spoke about a little bit earlier, your master controller or your primary controller or your slower controller is then going to be either just integral, or you can put it in as integral and derivative. We're probably just going to go for the integral. It does work, but it's not a very common configuration. Thank you for that question.
The QR code isn't working. If the QR code's not working, please use the link that I'm putting into the chat box. Oda, if you want more comprehensive material, you would need to join one of our programs. The links will be in the packet that we send you with this deck, but I will submit it right here in the chat box as well. So I've got that there. What is the impact of malfunctioning transmitter on the controller performance, and how to mitigate such?
Right, thank you for that question. The basic line is if you lose your controller, you lose your control. Okay, if the controller stops working, you've got a major problem. But fortunately, our PLCs and whatever we use, our DCS systems, our SCADA systems are very, very effective. Worst case scenario, you might look at redundancy, where you're going to have a spare controller that's going to take over. As far as the performance is concerned, the only thing that's going to affect you is if the signal that is coming in is very noisy, then you might have to put in some type of filtering. But the controller is going to do most of that. Thank you.
Any other questions? Give it one more minute. Is ALFC a PID application?
Right, that's a question that I can't answer because I don't know what ALFC stands for. It's not a common acronym that we are going to go and use in South Africa. I'm very quickly just trying to see if I can get something on ALFC control, just to go and see what that is going to stand for. And if it does answer me, then I can probably give you an answer about that. My system is just busy picking up. Okay, automatic low frequency control. Yes, that is then going to be a form of control that we can go and work with. The automatic load frequency control. That will then be a very specialized control, and I'm assuming that it's probably going to have some other type of PID loop in it. Probably would.
So 2 questions. One, which classes do you teach with us, Dr. Jacobs?
I have the pleasure of teaching very, very many classes. I've been with the parent company of EIT since 2004. They were known as IDC Technologies, and I was one of the pioneers doing the webinars, which we started back in 2011. I tend to stick to the instrumentation and the electrical items. So whether it's PLCs or SCADA or grid tuning or general instrumentation or electrical principles, I do mathematics as well. I've probably got about close to 100 courses that I do for EIT in many different areas.
Okay, so let's see. Would there be any impact or possible inclusion of AI in process control?
AI is absolutely brilliant. There most certainly is going to be. And please remember that AI is going to work on tons and tons of data. There is this fear around the world that AI is going to take our jobs away. And I would like to be the first person to say to you, no, it's not going to happen. AI is there to make our lives a lot easier. A lot of you use Waze on your phones to get around. That's got AI built into it. You know, you go and use these platforms to order stuff over the internet. That's got AI built into it. So AI is not going to take away our jobs. AI is there to look at a ton of data and come up with the best solution. I heard a wonderful explanation the other day, and that is, somebody that's living in poverty, if they were to go and ask AI how to improve their lives, AI is going to say to them, go and live in this house, go and live in that street. It's going to make decisions on the basic data that is available. A human being is going to go and say, I can't go and live there. I want to have a better life for myself. So AI is not going to replace our lives, but there is certainly going to be a place for AI in the world of process control.
Charlie says these processes are largely controlled within an automated ML, M2M, and IOL landscape, etc. Instrumentation networking similar to closed loop. Do you have courses taking these developments into consideration?
We do have courses that covers the communication. So if you were to go and do an advanced diploma, for example, in process control, there will be modules on the PLC side. There's going to be a module on process control. There will be a module on communication. There will be a module on protocols. That will get broken down into smaller issues, and that will be covered.
Esther has asked if you're available to assist with troubleshooting. I would say, Esther, that as an instructor with EIT, he's not available for work-related troubleshooting issues.
Absolutely correct. Absolutely correct. Remember, my employer is IT, and they have my total dedication and focus. You can understand that if I was to go and do consulting privately, it would not be fair to our clients. So it is an absolute no-no for me. That's just an ethical issue. Yes, there are people that would do it privately, but ethically, I am bound not to go and do anything behind the back of my employer, which is EIT. Thank you. It sounds very rough, but that's the simple answer.
Exactly. Charlie, we do have an Internet of Things course in the link that I provided before. Let me put it in again. Take a look at that and see if it's covering what you're looking at. Sarah asked this before. She's asking again, do you offer lectures on graduate certificate? So are you on the graduate certificate?
Sarah, I used to do the degree courses, but I have not got any at this point in time, and only because I have the craziest diary that you can imagine, and my diary just gets filled up all the time. So I prefer to do the shorter courses. These courses, I do 3-4 webinars and I'm out. Do another 3-4 webinars and I'm out. When I do the graduate courses, those courses are up to 6 months in duration. So I find that I tend to avoid those. But that's purely a personal choice. I have done them in the past, and maybe I will get back to them again in the future. But at this point in time, I don't do the degree courses. I do the certificate courses, I do the diplomas, and I do the advanced courses.
And we, the people who do teach our graduate degrees are also doctors in their fields. So they're excellent instructors all the way around. I'm going to take this as the last question. Is there a system that uses both automatic and manual control at the same time?
Right, that is another wonderful question. And I'm going to say to you, remember the early part of my demonstration when I showed you a SCADA system or a DCS? That SCADA or that DCS system is going to have hundreds of loops inside. Some of the loops will be in manual and most will be in automatic. So that's going to use auto and manual at the same time. But each controller is either in manual or it's going to be in automatic.
And Bharath, this one's for me, and we're going to close this off after this. And let me, before I answer, post this one more time, the link to get your certificate. So if you have been on the industrial automation course for more than 6 months, then joining another, and you're managing well, joining another course is perfectly fine. You haven't been doing it for that long, I'm assuming you're on an advanced diploma. If you're on a professional certificate, we definitely encourage you to join a second one. You won't have any problem managing that if you're not having trouble managing the first one. Fees are based on your location for currency and on the type of course that you're looking at. So you need to visit the page of the course that you like. There's a fees box. Click on it, choose your country. It will give you the fees. Okay? Thank you again, Dr. Jacobs. I'm going to wrap this up now, and if you guys have any other questions, you can put them in a general inquiry, and our team will route them to the right person, okay? Thank you all.
Welcome to this Yokogawa e-learning module. This module covers process control instrumentation. We will start this session with a short introduction of the key concepts and terms used in process control. After this module, you should understand why instrumentation plays such a key role in modern process control, both in terms of safety and quality, and also the impact that these instruments have on operational costs. We will present the most commonly measured process variables such as pressure, temperature, and flow. Finally, we will also show that the design of modern instruments makes them capable of measuring multiple variables, and therefore knowledge of their operating principles plays an increasingly important role in designing new projects. A process is broadly defined as an operation that uses resources to transform inputs into outputs. A typical example is an oil refinery where crude oil is transformed, through a series of steps, into gasoline. The example shown here is a summary of how a process in a plant is organized. A process can be split into 3 interconnected layers. The first layer consists of the sensors and transducers, commonly referred to as process instrumentation. These instruments measure the variables of interest at each step of the process. The second layer is made up of the final control elements, typically control valves. These instruments use the outputs from the sensors to adjust the process as needed. Incidentally, this diagram is of a real installation called a demonstration loop. The real flow loop will be shown later in this course. It is important to understand the relationship between these 3 layers as they are in constant communication with each other. This constant exchange of messages and information ensures that the users get the best results out of their process. In every process, there are certain objectives that are required. A process must be designed and operated to be safe at all times, to constantly produce the desired amounts of high-quality products, and last but not least, to remain profitable. This is a difficult balance that requires good engineering practices at the design stage. One such practice is selecting a measuring process instrument that is safety is in a given process, as accurate and reliable as possible, and able to maximize ROI. It is also important that the instrument be selected according to the process variable it will be measuring and the application requirements. Sometimes these guidelines are not followed sufficiently, which can result in catastrophic consequences. There are many variables that can be measured during a process, including temperature, pressure, flow, density, level, pH, and conductivity. These variables form the core of every industrial process. Additionally, some applications call for the measurement of more specific variables such as concentration, viscosity, and turbidity. However, the first 7 variables are the most commonly measured. This is the flow rate that was once used to illustrate the process layers. As previously stated, one instrument can measure several variables. For example, a Coriolis flow meter can measure both mass flow and density at the same time, while a differential pressure transmitter can measure both the pressure and the flow. This is another way of visualizing the different process layers, with the control system on the right communicating with the different instruments on the left. In the middle, you can see various protocols used to allow communication between the control room and the instruments, including HART, Foundation Field Bus, ISA 100 Wireless Standard, and Profibus. The choice of a particular protocol, much like the choice of a measuring instrument, is determined by the application. Ecogoa has extensive knowledge and can offer solutions in all aspects of process control. We have now established that process instruments measure variables. However, it has also been shown that the same variable can be measured by more than one instrument. Instruments differ in how they measure variables. A Coriolis flow meter uses Coriolis acceleration, whereas a magnetic flow meter uses Faraday's law, but they both measure flow. How an instrument works, its operating principle, also influences whether it can be selected for an application. To understand instruments' operating principles, you need to know what variables are measured and how these variables interact with one another. For example, the first step in selecting a temperature measuring instrument is to understand what temperature is and what it means. This concludes our module on the basics on process control instrumentation. For more information or to contact us, please visit our website and official channel on YouTube. Thank you.
My name is Hussein El Junaidi. I am a senior process engineer at Zohr gas field, which is the largest gas field in the Mediterranean in Egypt. I'm a former engineering section head at ProServe Egypt, and here is my email if anyone would like to contact me for any clarification or any technical question or anything needed. Okay, this will be our index for today. First, we will start to take an introduction about the oil and gas itself. What is the oil and gas? After that, we are going to speak about the composition of oil, crude oil, and the types of crude oil. After that, the grades of the crude oil. What are the grades, and how we know which grade is good or bad? What is petroleum refining? After that, we are going to talk about gas, natural gas composition and types, phase behavior, natural gas properties, and gas contaminants. After that, we are talking about an overview of gas processing. As I mentioned, some of information will be maybe repeated, but experience that it's just an introduction, not a detailed course about the oil and gas processing. Okay. The oil and gas, introduction to oil and gas. The oil and gas are a mixture of naturally occurring hydrocarbon compounds. Hydrocarbon compounds are mainly compounds combined of carbon and hydrogen. And these compounds are found in rocks, some sort of rocks, which has been formed thousands or maybe millions of years by the heat or the pressure, which turn the organic compounds or organic matters, such like living organism or organisms or living animals to an oil and gas. The oil and gas are found in reservoirs. This is a typical reservoir. There is a lot of types of reservoir, but this is a typical one. And we are not going today to talk about the type and the kinds of all reservoirs, but this is a typical reservoir. And some reservoirs are found on shore, which means inland, on land, and the others are found under the sea bed, which is called offshore reservoirs. The reservoirs mainly, this is associated gas reservoir. It consists of water and oil and gas. The compounds or the phases are mainly like just must be like that because of the density of the water is higher than the oil and the gas as well. After that, the oil compositions and types. In general speaking, there are two types of oil. Conventional oil, which is found in a form of vertical shafts that, like a pool, like that we showed here in the previous slide. Just a vertical, you have to drill only the well and start sucking the oil from the reservoir. And there is other unconventional oils which need special technologies and need more cost. And it's not easy to extract oil from unconventional oil sources, which is like oil sand and shale oil and heavy oil. The next picture will describe the conventional and unconventional oil and gas wells. Look at this side. This is conventional non-associated gas. We will know what is the non-associated and the associated in the next slides. This is conventional. It's easy to extract the gas. Just you have to drill the well and extract the gas from the reservoir. And there is also a conventional associated gas well reservoir, which you can easily extract the gas and oil. Here down is the sand stone, which is tight gas sand or sandstone, which is unconventional oil or gas well. You have to make a directional drilling, maybe horizontal drilling, to extract this oil or gas, which is more costly and is not easy to extract.
Are you coming towards the end of your career? And you're starting to worry that you've run out of time to build the life you always wanted? I got to 60.
Okay. The composition of oil, the crude oil is a multi-component mixture. It's consisting of about 108 compounds. And the typical composition of crude oil is about 90 to 98 hydrocarbons, 0.2 to 3.5 nitrogen and oxygen. And when we say nitrogen and oxygen, it's not pure nitrogen and oxygen. It's nitrogen compounds and oxygen compounds. Oxygen compounds such like alcohols and esters and ethers maybe. Also the sulfur is exist, maybe or maybe not exist in the crude oil. The percentage is 0.5 to 6%. And also when we mention sulfur, we are mentioning sulfur compounds. It's like H2S, mercaptans, and so on. So the composition of oil mainly as we mentioned, hydrocarbon, and there is a lot of types of hydrocarbon, such like the paraffins, olefins, naphthens, and aromatics. And when we start to extract an oil from anywhere, we have to make something called fauna analysis. Fauna analysis just telling us how much content of paraffins, olefins, naphthens, and aromatics exist in the oil which we are extracting. And there is other non-hydrocarbon compounds such as sulfur compounds, nitrogen compounds, oxygen compounds, and some metal like nickel, vanadium, and so on. Okay, let's talk about paraffins. Paraffins are also known as alkanes, and they are saturated compounds. And when we say saturated, it means it has only a single bond, no double bond exists in the compound. The paraffins are like methane, ethane, pentane, and is a straight chain compound with no double bond, saturated compound. And there is also isoparaffins, which is a branched paraffin, such like this one. This is branched paraffin. It's called isoparaffin. And the difference between the paraffins and isoparaffins in the properties, physical properties. The composition or the chemical construction or structure is the same. Same hydrocarbon, same carbon atoms and same hydrogen atoms, but it's the difference in the physical properties. This is an example. The pentane boiling point is 36, but the other isomers of the pentane are different in the boiling point, which is very significant. We must consider this when we are dealing with the isoparaffin. It's changing in in the physical properties. The other compounds exist in the crude oil are the olefins, but generally the olefins are not presenting in the crude oil as a crude at the beginning in the well. However, they are formed during the processing, like the dehydrogenation of the paraffins and naphthens. And the olefins are not saturated compounds because they have a double bond. They are not saturated and are going to form a lot of compounds and reactive. They form polymers. They are making a lot of problems in the refineries when they are existing. The other type of compounds are the naphthenes, which are cycloparaffins. It's also non-saturated. It's also saturated, sorry, which have single bonds, no double bonds. And also they are not reactive and naturally exist in the crude oil. The last one is the aromatics. Aromatics are non-saturated compounds, and it's very important in the refinery to increase the aromatics content in the final products because they increase the octane number of the fuels, such like gasoline and kerosene and so on. So the aromatics are very important in the refinery. The examples about aromatics is benzene, toluene, and xylene, which are the most popular compounds, aromatic compounds exist in the oil and gas. The grades of crude oil. The crude oil is categorized based on two things. One thing is the density, which we refer here to the API gravity, and there is a formula to calculate the API gravity from the specific gravity of the crude oil, and also the sulfur content. Let's look at this graph here. There is the grades of crude oil based on their sulfur content and the API gravity. As the API gravity increase, the density of the oil decrease. And as the API decrease, the density of the oil increase. And whenever the API gravity number is high, which means crude oil is more light and more good for the refinery, and no need for more processing or a lot of processing to extract the valuable components from it. And the grades here, like the Mexican oil, the Croatian oil, the UAE, and the Brent and the Texas oil, it's all depends on the gravity and sulfur content. We can see here the Brent and the Texas oil are most valuable crude oil. That's why their price is high, because they are light in the API gravity. Their density is light, and the sulfur content is low, which means they are sweet crude oils, not sour. Okay, here's a good picture describing the difference between the lower API gravity and the higher API gravity. You can see that the lower API gravity means high density, and the crude or the oil is like that, and the higher API gravity means low density, which means the crude is more light and visible. Okay. As you mentioned, the less refining a crude required, when the crude required less refining when it is light and have no sulfur content, or a little sulfur content. That's why it's considered less refining required. So this means its value will increase when it's need a small amount of processing, not very large amount of processing, not complicated process to refine the crude oil. This means it's valuable, and its price is high, as we mentioned before. Also, when the sulfur content is high, this means it's difficult to refine the crude oil, and it need further processing, which means its price will reduce because of the processing required. Okay. What is petroleum refining? When we talk about oil and gas processing, there is two types of oil processing. Oil processing, one is preliminary oil processing. It's done maybe in the site or at the platform, which is maybe desalting or heat of treater as a field, just to remove the salt, to remove the water if it exists. This is the preliminary processing. But after that, to take the valuable product from the crude oil, you have to refine the crude oil. So what is the petroleum refining? The petroleum refining has one goal, is to convert as much as of a barrel of crude oil into a transportation fuel. This is the goal of the refinery, is to convert as much of a barrel of crude oil into a transportation fuel. And transportation fuels have a boiling point ranging from 25 to 350 degrees Celsius. Okay, so let's check here how much transportation fuels are taken from the 1 barrel of oil. The most of crude oil is converted to gasoline. This barrel is 42 gallons or 159 liters, and these numbers are in gallons. Okay, these numbers are gallons. So from 42 gallons, there is around 20 gallons are converted to gasoline, and then about 10 gallons are converted to diesel, and some other products like fuel oil, like asphalt, like these products like coke are around 7 gallons, and there is heavy oil, LPG, jet fuel. Jet fuel is around 4 gallons, is 42 gallons. Let's check this small video about the barrel of oil and the final product.
Oklahoma State is such a unique place where we have students from all across the world.
Being a student on
around 40% is gasoline, and 25% is distillates, which are fuel for trucks, trains, and heaters, and kerosene and jet fuel. Around 10% of the crude oil barrel, which is very valuable, and then about 2% is residual fuel, which is also used in the tankers and the power plants, and about 1/5 of the barrel, 20%, is used as propane, naphtha, asphalt, and so on. So again, what is petroleum refining? Petroleum refining is about a combination of physical and chemical process. Can anyone tell me what is the difference between physical and chemical process? I'm waiting for your answer.
Can you answer with verbal or with voice?
Again, the voice is not clear. Can you repeat?
Can you hear me now? No?
Can you speak English? Does anyone know what is the difference between physical and chemical process?
Can I say?
I'm waiting for your answer.
Can I say?
Yes. Go ahead.
In the physical processes, they change the physical properties like heat, density, or like physical properties. But in the chemical processes, we change the chemical structure of the compound, and or react with other compound.
You are very close, but let's say that in a physical process, we are not changing the properties of the matter. We are not changing the properties of the matter. But in the chemical process, we are changing the structure of the matter, like the crude oil, like the alkylation, for example, process. We are changing the properties of the matter, changing the matter from A to B. This is the chemical process. But in the physical process, we are not changing the properties of the compounds or the components. Okay? So the dominant physical process in the refinery, or the main process in any refinery, is the distillation process. And this is the most important process in the refinery, because it enables separation of five components from major components, and it's about 70% of the refinery operation is the distillation process. And chemical processes such like alkylation and isomerization, and it's also very important in the refinery, because they are their value comes when you are going to increase the yield of fuels such like gasoline or kerosene, or when you are going to increase the octane numbers of the fuel. As you mentioned, the aromatics are very valuable when it comes to blending and increasing the octane number. There is the value of the chemical processes in the refinery. And also there is a lot of other processes such like desulfurization, dehydrogenation. It's also required to remove the contaminants of the crude oil. Here, when it comes to a chemical process, using the catalyst, using so on, this is the importance of the chemical processes in the refinery. Okay, let's move on. This is a typical distillation tower in the refinery. As we mentioned, this is the most important process in the refinery, which is consists only about heating and a distillation column. And it based on a variation in the boiling point of the components between the gases and the gasoline, naphtha, and kerosene. There is a different boiling point at which each component or each group of components boils, and this is the main concept of the distillation tower: is separate the components based on their boiling point. And from this, the components, each component going for a further processing and further maybe reforming or blending. Okay. If anyone has any question at any time, please raise your hand or just say it. No problem. Okay. This is a typical refinery. The most important, as you said, is the atmospheric distillation and vacuum distillation, and after that it comes to catalytic isomerization. Isomerization is, as we mentioned, changing the physical properties of the matter, changing the structure from paraffins to isobaraffins, for example, and this allow for a better octane number for the gasoline and the other flames. Hydrodesulfurization, for example, it's used to remove the sulfur compounds from the crude oil, and then catalytic hydrocracking. It's used to crack the heavier components into small components, which are valuable to the refinery and the products. All the cracking operations, such like the hydrocracking or catalytic cracking or thermal cracking, are the main purpose of them is to crack the higher or the heavy components into a light components, which are very valuable when it comes to the octane number and the gasoline blending and the other products blending. And there is a lot of processes which we are not going to talk about today because it needs more details and a lot of slides. But this is an overview of the processes. If anyone has any question, please say it, and let me check if we can answer your question. No one?
I don't have any questions, sir, right now.
Okay. Is it clear for everyone what we are talking about? If there anything is confusing, please let me know. And if there's anything is not clear, please let me know. Okay. This is, as we mentioned, a process overview of the refinery, crude oil refinery. Okay. Let's move on to the gas composition and the gas types. The gas is mainly, as we mentioned, is a hydrocarbon mixture. But the difference between gas and oil, the gas is very light. And it consists about from C1 to C7 plus components, no more. And it's very easy to process the gas compared to the oil. Okay, and the typical composition of natural gas is around 4% methane, around 4% propane, 0.5 methane, 0.15 methane. This composition differs from one reservoir to another, from one gas to another. But mainly the natural gas is methane. Mainly the natural gas is methane. Around 90% plus of natural gas is methane. Okay. There is two types of natural gas when we are talking about the reservoir. There's two types of reservoirs of natural gas. The first one is the associated gas, and the second is the non-associated gas. The associated gas exists with the crude oil. As we saw in the first picture, the reservoir consists of water, and above the water becomes the oil, above the oil becomes the gas. This reservoir, or this gas at this situation, is called associated gas because it's associated with the oil in the reservoir. Okay. The other type of gas is non-associated gas, which is a gas reservoir only. There is no oil in the reservoir, which at this point it's called non-associated gas. We may have water in the reservoir, but no oil. At this point, we call this reservoir non-associated gas. There is another definition for the rich gas. The rich gas means the gas contains heavier hydrocarbons. Heavy hydrocarbons, which is around C5 plus, not more than this C5 plus, which is in the normal conditions of pressure and temperature or liquid. Okay. Another definition: natural gas liquids, which are the components are separated in the normal temperature, the ambient temperature and pressure, are separated as liquids from the natural gas. And we will talk about the natural gas liquids in brief in seconds. Okay. And the natural gas liquids are very important because they are blended to the gasoline and the condensate and increase the octane number and the valuability of the crude oil in the refinery. Okay. Next, there is some important definitions. You have to differentiate between those definitions to better understand what we are talking about. There is one thing called NGL, which is natural gas liquids, and this is, as we mentioned, the liquids which are separated from the gas in the ambient pressure and temperature becomes in liquids. And there is two grades from the NGL, the Y grade and the X grade. The difference between them is the Y grade contains ethane, but the X grade doesn't contain ethane. And there is another definition which is LNG. There is difference between NGL and LNG. LNG is a liquefied natural gas, which is mainly methane, and it's liquefied at minus 162 degrees Celsius. After liquefaction, it's exported or shipped by tankers, and then we convert it to gas again. It's liquefied just to be easy for transportation, to easy for export. Here is a small question, and I need your answers about it. Do you know what is the volume of 1 cubic meter LNG when it converted to a gas? How will be 1 cubic meter LNG when it's converted to a gas? Can anyone answer this?
For 640 CV.
Thank you, but your story is wrong answer. Again the question. If I have 1 cubic meter of LNG, 1 cubic meter of LNG, how much will be the volume when I convert it to a gas state again? Can anyone tell me?
I think it's about 600.
Yes, correct. It's about 600. Can you imagine 1 cubic meter of LNG can be converted to a 600 cubic meter of gas when it's converted to a gas state? Okay. The other definition is the LPG, which is liquefied petroleum gas. The LPG, which we are using in cooking and heating inside the cylinders, this is the LPG. It mainly consists of C3 and C4, propane and butane. And the final definition is the condensate, which is the C5+, and this is very valuable in the refinery because it's going to be blended with the crude oil and the other light products. Okay, any questions? No. Let's move on. There is a very important curve to know about, which is the phase behavior of the natural gas. The phase behavior of the natural gas is a relation between the pressure, convection, and volume for each gas, and it's called a BGP diagram, or phase behavior envelope. And this phase behavior changing from one gas to another, from one reservoir to another. There is one phase envelope for each gas different from the other gases. Okay, let's take a look about the phase envelope of the gas. Here is the diagram of the phase envelope of one gas, and here is the temperature, here is the pressure. We have some important things to know about the phase envelope or about this diagram. The first one is the dew point curve, and the second one is the bubble point curve, and the pre-condenser, bar, and the critical point, the retrograde. First of all, the dew point curve, here is the definition for the dew point curve. This curve separates the pure gas from the two phase division. When we go back to this phase envelope, we can find that here is the gas only. There is no liquid exist at this region. And here is the liquid only. There is no gas exist at this region. And at this point, inside the dew point of the bubble point curve, here at this area, at this region, is called two-phase region, at which the gas and liquid can coexist with any different person. So the dew point curve, this is the differentiation between the gas region and the liquid region. And the dew point for each gas at a certain pressure or as a definition, the dew point at certain pressure is the first temperature at which the liquid starts to appear. In the opposite side here, you can find the bubble point curve, which also a differentiation between the liquid and the two phase regions. And also, as we mentioned, the bubble point bubble point pressure at a certain temperature, or bubble point temperature at certain temperature, is the point at which the first gas appears in the mixture. Okay, and the first gas appears in the mixture. We have also an important definition, which is Triton term here, which is the maximum temperature at which gas and liquid can coexist. Maximum temperature at which gas and liquid can coexist. And above this temperature here, there will be no liquid, no matter what was the pressure. Above this temperature, there will be no liquid, no matter what the pressure. On the other hand, here is the Triton bar, which is the highest pressure at which gas and liquid can coexist together. And also above this pressure, there will be no gas, no matter what was the temperature. Only would be a liquid above this point. And the critical point is the point at which the dew point and bubble point will meet, which is the critical point. There is an important definition here called the retrograde region. The retrograde region, simply, let's take an example. Here, the formation of liquid hydrocarbon in a gas reservoir as a pressure decreases. Let's take a look here. When we are the reservoir at this point, and we start to decrease the pressure at isothermal condition. Isothermal condition is the temperature response. Let's make an imaginary line here, means the temperature is constant at this point, and start decreasing the pressure, go like this. The liquid will start to appear. But in the normal operation, when we decrease the pressure, what will happen to the gas? Can anyone answer? If I have some gas and decrease the pressure, what will happen? Anyone? If I have some gas at certain pressure and decrease the pressure of the gas, what will happen at this condition? Isothermal containers contain some gas, and the pressure decreases. Condensation. when the pressure decreases, it will condense or vaporize? No, it will vaporize. When I have some gas, vapor, it's already vapor, and I reduce the pressure. When reducing the pressure, I increase the distances between the atoms. Can you please mute your mic? Okay, when I have some gas in a container, okay, and decrease the pressure. Decreasing the pressure means the distance between the atoms will increase, and this will never condense. It will never condense. It will vaporize or continue to be at the same state, which is gas. But this region is called retrograde because this is a reverse of what happened in the natural. Because when I decrease the pressure here, the liquid will start to appear or a condensation happens, which is not normal in the normal life or in the nature. That's why this region is called retrograde. Okay, it's okay. Did you understand or not? Anyone?
Yes.
Clear? Okay. So that's why they call this region retrograde, because it's not like the nature behavior. Okay. Yes. So this is the definitions we already mentioned: bubble point curve and dew point, critical point at which the curves meet, bubble point and dew point curves meet. Triton in turn and Triton particles. Okay, all definitions are done. Okay, so let's talk about the natural gas properties. The most important, one of the most important properties is the gas specific gravity. As you mentioned, the gas consists of a lot of components, and we cannot assume the gas density or specific gravity, but only we can calculate it. So we can calculate it by multiplying the summation of the mole fractions, each mole fraction, by the molecular weight of each component, and divided by the molecular weight of the air, which is 29 or 28.97. Here is an example for calculating the specific gravity of a natural gas found in some reservoir. Here, the gas consists about 87% C1, 0.084 of C2, 0.023 of C3, and CO2 0.016, and H2S 0.006. This is mole fraction. This is mole fraction, not percentage. Okay, how do we calculate the specific gravity? We calculate the specific gravity by multiplying each mole fraction with the molecular weight of the component and take the summation of all and divide it by the molecular weight of the air. Such like this. So the gas gravity will be the mole fraction multiplied by each molecular weight of each component, like this, and divided by 29, which will be 0.634. That's how we calculate the specific gravity of any gas, of any natural gas exists. Okay. The second most important property is the Z factor, or the gas deviation factor. The deviation factor is generally or simply it measures how the real gas deviates from the ideality. We know there is no ideal gas in the real life. So the Z factor is a measure of how the real gas deviates from the ideal gas. And we can calculate the Z factor from the chart, such like this one, by calculating the pseudo critical pressure and pseudo critical temperature from the summation also of the mole fraction. You know the critical pressure for each component is known. methane مثلا, for example, for methane is known, for ethane is known, but we cannot calculate the critical pressure for a natural gas mixture, or we cannot assume, I mean. So we can calculate it by also multiplying the mole fraction of each component by its critical pressure, and also the critical temperature is the same. After that, we can get the reduced pressure and temperature based on the operating pressure and temperature of the gas. This will allow us to enter the curve and define the Z factor of the gas. So this is just calculations to define the Z factor of the gas, or how this gas deviates from the ideal gas in properties or in characteristics of the gas. And there is also correlations and software to obtain the critical pressure and temperature for the mixture. And it's not mentioned here, but there is a lot of correlation software to calculate the critical pressure and temperature. And if you are using Alton Hysus or Alton Plus, it will be calculated automatically. Okay, and this is the most important property: the chemistry or specific gravity of the gas and the Z factor. No need to mention, there is a lot of other properties, but we are not going to mention here due to the time limitation. But those are the most important properties of the natural gas. Okay, let's move on. What is the gas processing? Okay, the gas processing or processes can be broken into two major categories. The first one is to remove the contaminants of the natural gas, because the natural gas comes with some contaminants we will mention in a while. So we need to remove those contaminants from the natural gas to be able to be sold in the market. And the other thing is to remove the natural gas liquids or the condensate exist in the natural gas, because they are valuable compounds or valuable products, can be sold separately or can be added value to the gas plant. So there is two types: removing of the contaminants or removing of the liquids such like NGLs or condensates. Okay, what are the contaminants of the natural gas? The main contaminants are the water, hydrogen sulfide, and non-combustible inert gases such like the CO2 and nitrogen. We will talk about each one in brief here. So, and there is other contaminants, maybe or maybe not exist, such like solids, oxygen, mercury, helium, and norm, which is naturally occurring radioactive materials. Maybe exist or maybe not. And also the hydrogen sulfide maybe exist and maybe not. And by the way, when the hydrogen sulfide exists in the gas, we call this gas sour gas. And when there is no hydrogen sulfide in the gas, we call this gas a sweet gas. Sweet gas. Okay. What are the problems of the water? What problems can water make to our gas? The first and the major problem is the hydrate formation problem. The hydrate formation or hydrate are something like ice are formed in the pipelines at specific pressure, mainly high pressure and low temperature, and cause a lot of problems, such like blocking of the pipeline. They reduce the volume of the pipeline and also reduce the amount, allowing you not to produce or to take all production from the pipeline. The size of the pipeline will reduce, and you cannot take all the production from the pipeline. Will be a limited volume of the pipeline, and also the water cause corrosion to the pipeline, and as we mentioned, blockage. This is a picture of the hydrate formation. Maybe not a total blockage, but as I mentioned, it will reduce the volume of the pipe, and you cannot make use of the whole volume of the pipe for the production. Okay, and this also is a vector for the pollution caused by water. Next is the hydrogen sulfide. Why we need to remove the hydrogen sulfide from the because it's a toxic gas and corrosive gas, and also we need to remove the hydrogen sulfide because we need to keep our environment clean and safe. Maybe some of you know or some don't know, the hydrogen sulfide is very toxic gas. Let's take a quick overview about what will happen if you exposed to H2S. Those numbers are in ppm part per million. It's a very small amount. The H2S has the odor of rotten egg up to 10 ppm. After that, you cannot or you never smell the H2S. It will be a silent killer above the 10 ppm. From 10 or 20 to 100 ppm, it will cause irritation to the eyes, and the breathing will not be very well. Above the 100 ppm, there will be severe irritation of the eyes, and the cough and breathing will be very, very hard. Above the 25 ppm will be very difficult to breathe, and maybe you lose your coordination or lose your consciousness. Above the 500 ppm, it will be very struggling to breathe.